Hello and welcome to another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 4, Lesson 7 on Mapping Similarity. Now, that's an interesting title, Mapping Similarity. Now, I'd like you to remember that back a few units ago, we did a very similar lesson on mapping congruent figures. And basically what we said was, look, if I've got these rigid motions like a reflection, a rotation, or a translation, and I can find a combination of those, or maybe just one of them, that will map one figure so that it moves and sits exactly on top of another one, then the two figures must be congruent. Well, today we're going to do something very similar in that we're going to try to use a dilation along with maybe one or more of those rigid body motions to get one similar figure to then sit on top of another similar figure. So let's get right into that in the first exercise. When two figures are similar to one another, we can use a dilation and possibly a combination of rigid motions, and again those are translations, reflections, and rotations to map one figure on top of another. And again, that term, map one figure on top of another, just means that the image of the one figure lies exactly on top of the other figure. So let's take a look at that in exercise number 1. In the diagram below, triangle ABC is similar to triangle ADE. Specify a dilation, both its center and scaling factor, that would map triangle ABC on to triangle ADE. All right, so in other words, this triangle ABC is similar, I'm telling you, is similar to triangle ADE. All right? The question is, what dilation would sort of, if you will, stretch triangle ABC so that it then sits exactly on top of triangle ADE? Well, one thing please note in this problem, is that we really don't want A to go anywhere, It's part of both triangles, It's this point. And whatever dilation we choose, whatever center we have, and whatever scaling factor we have, we don't want A to go anywhere. But we do want B to get mapped to D, and we want C to get mapped to E. Now, the fact that we don't want A to go anywhere tells us something for certain. It tells us that A should be the center. Because remember, in a dilation, the center doesn't go anywhere. So to begin with, we want our center at point A. Now, for a dilation, you really just have to specify two things. You have to specify the center, and in this case, we want the center to be A. And you also have to figure out what the constant of dilation is, the scaling constant. I'd like you to pause the video now and see if you can figure out what the value of K is, and it is going to be fractional. All right, well, remember, to figure out the value of K, we always want to take sort of like a length that's from the, quote, new triangle divided by a length from the old triangle. And keep in mind, we're trying to get triangle ABC to expand so that it maps on triangle ADE. So the easiest way to calculate K is to simply use these two lengths, Where the 9 is the new length, It's what we want to map on top of, and the 6 is the old length. So K just should be 9/6, which, if we divide both top and bottom by 3, gives us a dilation constant of 3/2. Or, if you like mixed numbers, 1.5, or if you like decimals, 1.5. All of those are fine. And that's it. And you could literally kind of visualize it, We kind of pin down point A, and we start to stretch the rest of the triangle ABC out, C just slides along, this ray AC until it lands on point E, and B slides along this until it lands on point D, and that means that CB would then slide until it lands on ED. And A doesn't go anywhere. And that's it. Now that's a very simple mapping of similarity, And it's simple because all we had to do is do a dilation. We didn't have to bring in any rigid motion like translations, rotations, and reflections. The rest of the lesson, we kind of want to get into those as well. So let's play around with these ideas more. All right, let's go coordinate plane. Sometimes to map one similar figure onto another, we need to use not only a dilation, but also one or more rigid motions. Let's see how that works in the coordinate plane in exercise number 2. On the grid below, triangle ABC is similar to triangle EFG. Answer the following questions. Letter A, what is the scaling factor needed to map ABC on to EFG? How can you find it? All right, so I'm claiming that this triangle and this triangle are similar, and they should kind of look like it, right? They're roughly the same shape, right? And that's similar figures are the same shape but different sizes. First thing I'm trying to figure out is what scaling constant I would need just simply to get this thing the same size as this thing. Pause the video now and see if you can figure that out. Well, what we really want to do to figure out that scaling constant is we want to take one of the 3 lengths over here and divide it by the corresponding length over here. Now, the lengths of the 2 slanted sides are actually difficult, but not impossible to figure out. The side length, though, that would be very easy to figure out is EF and BC, right? Because they're horizontal, we can literally just count off, squares in our grid. And in fact, what we can say is that EF is 8 units long, BC is 4 units long, right? So we can say that our K, right, is going to be 8/4 or just a dilation constant of 2. And again, we just got that by taking the length of EF and dividing it by its corresponding length BC. Now, again, you might ask, well, why did we know to do this divided by this instead of this divided by this? And that's all about the fact that we're mapping ABC onto EFG, right? We're taking the smaller one and we're making it into the larger one. If we were trying to map this one back to this one, well, then it would be 4 divided by 8, and the scaling constant would be 1/2 in that case. Now, let's take a look at part B. If triangle ABC was mapped using a dilation with a center at A and a scaling factor from A, show where each of its vertices would be mapped to. All right, so this is a little more challenging, right? Because what we're doing now is we want to take this particular triangle, all right? We want to pin A down and we want to stretch out these sides by a factor of 2. See if you can figure out, you may need a ruler for this, or you may not. See if you can figure out where each one of those 3 vertices to go if we have A as the center, right, and we dilate using a constant of 2. Pause the video now. All right, well, A is the center. A is the center. So A's not going anywhere, right? A prime is going to be -9, 7, because it is the center. And under a dilation, the center doesn't go anywhere. Now, this would be so easy if the center was at the origin, but the center isn't at the origin. And because the center is not at the origin, we have to work at this a little bit harder. If I want to figure out where B prime goes, then what I'm literally going to do is I'm going to look at A and I'm going to say, well, what do I have to do to go from A to B? Well, I have to go down 3 and to the right 2. Right? If I want to stretch B prime so that it is twice as far from A as where it started, then I should go down another 3 and go across 2. So 1, 2, 3, 1, 2, and this 1, 2, 3, 1, 2, 1, 2, 3, 1, 2. This should be B prime, right? It's going to stretch down to here. All right, and B prime then should be at -5, 1. All right. And likewise for C, right, I want to think, all right, well here, right, to go from A to C, I'm going to go right 6 and down 3. So again, to stretch it twice as far out, I'm going to go again right 6 and down 3. Right? Yeah, that's definitely right. 6, 1, 2, 3, 4, 5, 6, 1, 2, 3. Very messy. All right, and that's going to be C prime. And that is going to be at 3, 1. Okay? Now, it should look pretty obvious, although quite messy, that this triangle and this triangle, right, are congruent to each other. All right? But let's talk in letter C about why we now know that triangle A prime, B prime, C prime would have to be congruent to triangle DEF. Well, it's this simple, right? Two figures are congruent if their angles are the same and their side lengths are the same, right? Well, we know that the angles were the same because the angles are equal when we've got two figures, right, that are dilations of one another, or that are similar to one another. So the angles are congruent because similar triangles have congruent angle pairs. But we also know the sides are congruent because of the dilation. All right. In other words, we ensured that by dilating by a factor of 2, we now made all the side lengths of this triangle equal to all the side lengths of that triangle. But keep in mind, the whole idea of a similarity transformation is that we would map this triangle on top of that triangle. And although the two triangles are now congruent, A prime, B prime, C prime, and actually let me call that A prime right now, even though A and A prime are in exactly the same place, right? Even those two triangles are congruent, they're not sitting on top of one another, right? So let's take a look at letter D. Letter D. What transformation would you need to now map triangle A prime, B prime, C prime onto triangle DEF? So, there we go. Couldn't get my board to go back up. What do you think? What would I have to do to take this triangle now? Let me try to outline it a bit better. What would we have to do to map this triangle now so that it lies on top of that one? Pause the video and think about what rigid body motion would be needed. Well, it would have to be a translation, right? All I'd want to do is I'd want to move this thing over to the right 1, 2, 3, 4, 5, 6, 7 units, and then I'd want to move it up 1 unit, right? So a translation that moves this to the right 7 and 1 up. Fit it right in there. A translation, 7 units right, and 1 unit up. And there it is. So all in all, right, if we had to describe the similarity transformation, we would say, well, it would be a dilation with a factor of 2 centered at A, followed up by a translation by 7 units to the right and 1 unit up. Now, I will say, whenever you've got like this combination of like a dilation and a rigid body motion, very often it's not unique. In other words, I could have actually started by taking this thing and translating it 7 over and 1 up, and then dilating it now using point D as its center, but continuing to use a scaling factor of 2. And we're going to explore that kind of different order thing in the next exercise. So let's do that now. Let me try to find a little spot to move that. Here we go. All right, let's take a look at exercise number 3. In the grid shown below, triangle MNP is similar to triangle ABC. We want to map triangle ABC onto triangle MNP. And let's pause for a minute just to make sure we got that. We want to map this one onto this one. So we're going to go from the bigger triangle and we're going to somehow try to get it to the smaller triangle. Letter A asks the following. Besides a dilation, which other transformation seems to be involved? What do you think? Which other transformation seems to be involved? Pause the video now and try to answer that question. Well, I hope it's rather obvious that it is a reflection across the x-axis. So if I take this and I flip it up, right, then at least the two triangles are kind of oriented in the same way. So a reflection across the x-axis. All right, kind of keep that picture in view. Let's take a look at letter B. Map triangle ABC using the transformation from above, i.e. the one in A. Draw it on the grid and state the coordinates of its vertices below, label as A', B', C'. All right, well, this is a great review problem. Why don't you take this triangle, reflect it across the x-axis, plot the new triangle, A', B', C', and show that kind of mapping down here. Pause the video now and go through it. Now you could count squares, but keep in mind that anytime I take a point, let's say down here, and I flip it across the x-axis, what happens is that the x-coordinate stays the same, but the y-coordinate changes its sign. In other words, I can actually come up with all of these and then plot. So let's do that, right? So A', right, when it gets reflected across the x-axis, again, the 4 stays the same, but the 3 changes sign. B' the same way will be 12, 3, and C' will be 4, 7. So let's do some plotting here. Let me get that out of the way. A' is 4, 3, which lands it right on M. B' is 12, 3, right there. And C' is 4, 7, which lands it right there. So I'm gonna draw that triangle in. Just freehand it. That should be good enough. All right, cool. So we just take this thing, flip it up here, and now, of course, A', B', C', right, is congruent to ABC because the reflection is just a rigid motion. Now, let's take a look at letter C. Specify a dilation, both its center and scaling factor, that would map A', B', C' onto triangle MNP. So this is important. At this point, I want to completely ignore this one. I'm just looking at this picture. I want to know both a center and a scaling factor that would allow me to take A', B', C' and kind of shrink it down, if you will, so that it sits on top of MNP. See if you can figure out both the center and the constant of dilation. All right, well notice, right now, A' and M are sitting on top of each other, and we don't want A' to move, right? Because it's already where it should be. A' is sitting on top of the point where I want it to be mapped to in the end of this problem anyway, so A', in other words, or point M, or the coordinate 4, 3 is our center. All right, so we could say a center at M, or A', or 4, 3, any of those would be okay. Any of those, because M, A', and 4, 3 are all the same point. That's where I want my center. Now the harder part is the scaling constant. But what we should know immediately is that it's got to be less than 1. And it's got to be less than 1 because we're going from a bigger triangle to a smaller triangle. Now, you've got really two nice choices for it. You can either use the length of MN divided by the length of A', B', or you could use the length of MP divided by the length of A prime C prime. And actually, let's take a look at those two. I'm gonna actually do them both. So just to show you that it doesn't make any difference. So let's start with this one. Let's do Mn, which is 6 units. So K would be equal to Mn divided by, let's just make sure, A prime B prime, A prime B prime. Mn is equal to 6 and A prime B prime is equal to 8, and of course that would reduce down to 3/4. But you could also, right, you could also do MP divided by A prime C prime. So MP divided by A prime C prime, right, it's always the new length divided by the older length. MP is 3, A prime C prime is 4. So no reducing necessary, but look at those two, the same scaling factor. Always, always, always the final length divided by the initial length, the new length divided by the old length, etc., etc. And keep in mind, again, you know, we're trying to go from this larger triangle A prime, B prime, C prime to the smaller one MNP. So Mn divided by A prime, B prime, or MP divided by A prime, C prime. Now, there is no reason we have to do the reflection first and then the dilation. And that's kind of what letter D gets into. Let's take a look at it. If we did the dilation first, what portion of the dilation would change? All right, so we need a reflection and a dilation. But if we decided, instead of doing the reflection and then the dilation, if we decided to take this thing and dilate it first and then reflect it, what would change about the dilation? And remember, dilations only have two things. They have their centers and they have their dilation constants. Which one of those would change? Pause the video now and think about this for a moment. All right, well, the plain fact is that the dilation constant wouldn't change, would not change. It would still have to be 3/4, because ultimately if we need to get this triangle to be the same size as this triangle, the smaller one that is, then we've got to have a dilation constant of 3/4. So the only thing that would change would be the center. And again, the center at that point would likely be point A. All right? So if we, shrunk this thing down so that we dilated it first and it ended up looking like this, right? This is what it would look like if we used point A as the center and dilated it by 3/4, then we could take this and just flip it over and it would immediately lie on MNP. All right, and that's the thing that's tricky. If they just ask you this question kind of just right out in the open, then you could do it in either order, but certain things would change and certain things wouldn't, like the scaling factor. All right, let's take a look at one final problem. This one's kind of cool and pretty challenging. Exercise number 4. Triangles EFG and QSR, nice, actually it should be QRS, sorry. EFG and QRS, I apologize, not QSR, and yes, the order matters, are similar. Specify a rigid motion followed by a dilation that would map EFG onto QRS. All right, so I need to find a rigid motion first, then a dilation second, and that's a lot, I've got to do a lot there, that will get this triangle to map onto that one. So pause the video now and see if you can describe these in as much detail as possible. All right, I want the rigid motion first. Now, what hopefully is obvious is that the rigid motion is not a translation. If it did, then the orientation of this triangle would kind of roughly stay the same, but it hasn't. Likewise, it's not a reflection, because if it was a reflection across either axes, we could kind of see that wouldn't quite be right either. In fact, the first transformation, if we're going to go with a rigid body motion first, then what I need is I need a rotation by 90 degrees about the origin, right? And if I rotate triangle EFG by 90 degrees about the origin, it lands right there. So the first thing is a 90 degrees counter clockwise around the origin. All right, now what's my dilation? Well, notice, right, that right now we've got that point, which used to be point F, I guess now it's point F prime, is sitting on top of R, right? That's my center. Anytime you've got these two triangles, one of them sort of embedded in the other, whatever point they share in common almost always is the center of dilation. So now we're going to have a dilation with a center at point R, okay? And then what's my K? Well, again, we should use easy lengths, right? And I want to make this big triangle into this smaller one, okay? And the easiest lengths to use are the lengths of QR and EF. And remember, QR is my end goal. That's the one that I want. This is the one I'm beginning with. So K is going to be equal to QR divided by EF. QR is 3 units long. EF is 6 units long. So I need a dilation constant of 1/2. All right, so I first rotate by 90 degrees, then I fix point R, and I shrink everything down by a factor of 1/2. That's kind of cool, right? But what happens if I do it in the opposite order? And that's letter B. Let's take a look at letter B. Specify a dilation followed by a rigid motion that would map QRS, again, my apologies, QRS onto EFG. All right, so let me move this thing back. All right, so now I want the dilation to come first, all right, which means I've got to specify a center and a constant, and then I need the rotation, it's going to still be a rotation, to come second. See if you can describe those two. All right, well, we know that when we rotate this by 90 degrees counterclockwise about the origin, that point F gets mapped up to that point R. And I'd kind of like it still to do so after I dilate this, right? After I shrink this thing down, I still kind of want this point to get mapped up to that. So what I'm going to do in this situation is the first thing I'm going to do is dilate this triangle using F as a center so it doesn't go anywhere. And I still have to dilate it by a factor of 1/2 because all the lengths on this triangle are 1/2 the lengths on that triangle. So my first step is going to be a dilation with a center at F and K equal to 1/2. And when I do that, it's going to be tough because I can't really rotate this new one that I'm drawing right now. But when I do that, it's going to all shrink down to this thing. Because again, I'm fixing F, right? It's the center of dilation, it doesn't go anywhere. So I shrink all this thing down by using F as my center and a K of 1/2. And now, if I rotate that up by 90 degrees, that point is going to rotate up to here, this will rotate up to here, and this will rotate over to there. So the same rotation now. I'm now going to rotate by 90 degrees counterclockwise. By the way, that's okay to abbreviate counterclockwise as CCW. About the origin. This is some of the most challenging work we do with similarity and dilations. right? Because we've really got to it's like playing chess and having to think 2 moves into the future, right? I really have to think about 2 different things in these last couple problems that will map one triangle on top of the other. And to make matters more confusing, of course, one of them will depend on the other one, right? So like once you do one of them, things change, right? The center of dilation could change. The scaling factor won't, right? The scaling factor between one similar triangle and another is going to be 1/2 or 2 or 3 or 3/2 or whatever it is, regardless, right? Because that's just going to be changing the size of the figure, and it doesn't matter whether we do, whether we do it first or second, we still have to change the size by the same factor. All right, let's wrap this up. So in today's lesson, we looked at mapping similarity, specifically using a dilation, sometimes in combination with one rigid motion like a reflection, a rotation, or a translation, to get one triangle to map directly on top of another one. And again, that can be challenging, especially when there's 2 transformations involved, because then there's an issue of which order do you do them in. All right? But it's kind of an important topic and one that you'll certainly revisit quite a bit in high school geometry. For now, I just want to thank you for joining me for another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.